Hello, everybody. My name is Isaac Lobo. I'm a part-time honours student at Charles Sturt University, having done my bachelor's in Melbourne. And I'm also a full-time high school physics teacher. So I'm really happy to be here and not in front of my wild Year 8 class. So it's a much better audience. Today, my presentation's on the research I've been doing along with my supervisors, Alan Ernest and Matthew Collins, which is on quantum gravitational eigenstates in Navarro-Frank-White potentials. So it's a bit quantum-y. But there is an intersection with astronomy, so please stick around with me for that. So let me just dive into it. So there's a range of research recently as to either observing or applying quantum mechanical behavior, but on macroscopic scales. And one particular research of note is that done by Nesveshevsky, who in 2003 experimentally observed the stationary state of neutrons found by mirrors and also Earth's gravitational potential. Now, this kind of, I want to say, inspired researchers at CSU to look at similar systems. Well, can particles find themselves bound by gravitational potentials elsewhere? Yeah, but not on the scale of planets, like in Nesveshevsky's research, but rather in the much larger system of a galactic halo or near a galactic center. Yeah. And what this research found was, well, for some states in this potential, particularly those with low n minus L value, where n and L are the principal and angular quantum number, for states with low n and L, the transition from one state to another happens exceedingly rarely, very, very rarely. And that corresponds to very long lifetimes, sometimes comparable to the age of the universe, but also exceptionally weak interaction with light. Now, of course, since they're particles, they do have some gravitational influence, and so that might kind of bring some distant dark matter bells, but I'm not saying it is. You know, it's interesting. Okay. Now, this analysis was, of course, done with this particular potential, but what might serve as something a bit more accurate is if the potential was replaced with something which reflected the dark matter content of a galaxy. Yeah. And so one of the most popular and well-known dark matter density profiles is the Navarro-Frank-White, or NFW profile. Here, delta C, rho C, Rs are parameters of the profile corresponding to the concentration of the galaxy and the critical density, scale radius, so on. This can be converted into a potential by input into Poisson's equation. And so essentially, my research looks at, okay, could particles find themselves in bound states of such a potential? And if they could, what kind of behaviors would they exhibit? So, and this is the teacher in me, forgive me, my lesson plan for today is as follows. So, I want to talk about the first three of these points from a purely theoretical computational perspective. And then the last two, I'll discuss the more physical interpretation of what the theory suggests and some options for further research. So let me just dive into it. How were the eigenfunctions in an NFW potential determined? Now, it amounts to solving this particular three-dimensional radial Schrödinger equation. It's particularly ugly. And the results of this give you the radial eigenfunction. There is, of course, an angular and azimuthal component tacked on at the end, but this is the non-trivial part. And it is non-trivial. There is the expected centrifugal term, because we're in spherical coordinates, and of course the NFW potential itself. Now, there is no, as far as I know, closed algebraic solution to this equation. And so in order to find the eigenfunctions, I had to resort to, or the research team I'm working with, had to resort to approximation strategies, notably the WKB, and the lesser known modified area function. I'm going to call it the math approximation method. So I'm going to briefly describe each of these approximation schemes. You can read about WKB in most standard textbooks, but just a brief recap. The WKB approximation amounts to computing this particular integral, which depended on the energy. And computationally, what occurred was I calculated this integral between the turning points of the potential, and depending on whether the integral was greater than or less than the right side, the energy gets to fluctuate up, down, until it arrived at an energy where the result of the integral was equal to the right-hand side within certain accuracy margins. Now, in principle, you could just then take that energy and then input it into the WKB approximation for the eigenfunction in the classical region, and you'd be done. That's the eigenfunction. But there is a problem. The WKB procedure causes the eigenfunction to diverge rapidly near the turning points of the potential. So you could attempt to solve that by truncating the eigenfunction just before this point, and then match it across those turning points. You can attempt to match it across, but that introduces pretty unpredictable matching errors and continuity errors. So we didn't feel it was very reliable. So instead, we took that energy, and instead of putting it into that eigenfunction, we used the math procedure. Now, the math procedure amounts to treating the eigenfunction as a modulated area function here, where that modulation are given by these integrals. Now, details of this approximation scheme can be read about in quite a terse paper by Langer in 1931, and a slightly less terse, more approachable monograph by the National Institute of Standards and Technology, 1991. But the underlying principle is that it very tactically assumes the linearity of the potential near the turning points. And since area functions are solutions of a linear quantum potential, you avoid those divergences completely. So let's check if it's reliable. So to first check if it's reliable, instead of applying it directly to the NFW potential, I applied it to this potential here. It's already been well studied by research at CSU, but you'll notice it looks of a form very similar to that of like the hydrogen Coulomb potential. Yeah, and so solutions of this equation are analytic. They're Laguerre polynomials. So here is the approximated eigenfunction and analytic eigenfunction overlapped. There they are. So a good amount of overlap. Now this was done for 44 other eigenfunctions, and it was found that the overlap integral had an accuracy of 99.98%. So a very low error. Very, very low error. The reliability was also tested by computation of the Einstein A coefficient. And this corresponds to the rate at which a state will decay from state I to state F. And here are the transition rates, the analytic and approximated. The bold dots are the analytic results, and the approximated transition rate are actually directly behind them. They're indistinguishable on the plot, but it is a log plot, so it's not, don't get too excited. There is some error there, it's just a bit hidden. And this is the error, okay? So barring some initial fluctuation of the error, the transition rate error was around 1% using this approximation strategy. So the WKB math mix suggested that it can be used to analyze the NFW potential system. So finally, the key results from the NFW analysis. These are the transition rates. So I want to draw your attention particularly to this band of data. So on the vertical axis, you have the transition rate, the rate at which a state will go from one to another. And then on the horizontal, you have n minus L, principal angular number, n minus L. For states with very low n minus L value, the transition rate is very, very low, meaning they will seldom decay to another, they will seldom emit light. Physically, these states, however, have very low quantum numbers, like n equals 10, 20, 30. And so if they were physical systems, these particles will be way too close to the galactic center. And so that means there's way too much environmental interference, the coherence effects, the NFW potential is less applicable in that region. And so if instead these particles were to find themselves in bound states of the NFW potential, they would need very high n value to be far away enough from the environmental effects. But if those states also had high L value, it means the transition rate would even be very, very, very low. So the actual implications, as mentioned, states with high N and high L will have very low transition rate and so interact with light exceedingly rarely. However, they still exert gravitational influence. So they are dark matter-like. They're not dark matter. No, not yet, not conclusively, but they're dark matter-like. They have that kind of property. Since they have masses comparable to the proton, it means, or it's possible, that dark matter-rich galaxies may also be hydrogen-rich galaxies, and that's what was a point of my supervisor's talk earlier in the day. As points of further research, here are some examples. What all is decoherence wave? Where does the potential come from? How does it evolve? How do states actually form those high N and high L values? I have some thoughts about that. And of course, how do we test? But that brings my presentation to a close. Thank you very much for your time and for your attention. Open for questions. Cheers.